Hello friends and students. Welcome to my video tutorial, which is an excerpt of my past upload on the linear applications of Newton's three laws of motion. I selected this particular problem on static equilibrium to highlight a common misconception regarding the use of the trigonometric functions sine and cosine. Listen first to the explanations presented in the excerpt, and after which I shall give further explanations that were missed out in the original video. Problem number 5. A 1,130 kilogram car is held in place by a light cable on a very smooth frictionless ramp as shown in the diagram. The cable makes an angle of 31.0 degrees above the surface of the ramp, and the ramp itself rises at 25.0 degrees above the horizontal. Question letter A. Find the tension in the cable. And letter B. How hard does the surface of the ramp push on the car? Let the magnitude of acceleration due to gravity be equal to 9.80 meter per second squared. Alright, so examining our diagram, we already have the forces identified. Okay. First, we have the force capital T, which is the force exerted by the cable, okay, on the object, represented here by that dot. All right. So the force exerted by the cable on the car makes an angle of 31.0 degrees with the surface of the ramp. All right. So naturally, it will have the component Tx, which is directed uh, along the ramp, okay, along the ramp, but directed, of course, up the incline. And the y component, of course, is uh, directed perpendicular, upward perpendicular to the surface of the inclined plane. So we label it here as T of y. Of course, we have the weight of the car, W, all right, and the component of that weight of the car, Wy. So Wy is directed perpendicular also vertically, but downward um, along the defined y-axis. We define this as our y-axis, while the x-axis is along the uh, surface of the ramp. Right. So if the ramp itself makes an angle of 25 degrees, 25.0 above the horizontal, okay, by definition of similar triangles, this angle that is formed between the weight W and the y component Wy must also be equal to 25.0 degrees. All right. So for our solution, detailed solution of finding the tension T and also the force F normal, all right, we will look at the solutions in the next slide. So for our solution, okay, we determine the value of the weight W is equal to mg. Okay, the mass of the car is 1,130 kilogram. Multiply that by the value of g, 9.80 meter per second squared. So the weight of the car, okay, rounded to three significant figures, is equal to 1.11 raised to the fourth power Newton. And we determine the x component of the weight using the formula Wx is equal to W sine of the angle 25 degrees. Substituting, we have 1.11 times 10 to the fourth Newton multiplied by the sine value of 25 degrees, which is 0.423, and we get as the x component of the weight W in our earlier diagram that was supposed to be directed down the ramp. All right, so you may check on that in our vector diagram. So that value of Wx is equal to 4.70 times 10 to the third power Newton. Likewise, the y component of the weight Wy is equal to W multiplied by the cosine value of the 25-degree angle, meaning 1.11 times 10 to the fourth Newton multiplied by 0.906, and we get the y component of the weight equals 1.01 times 10 to the fourth power Newton. We also determine the x component of the tension T. All right. So we express that as Tx equals T cosine of the angle 31.0 degrees. So, since we still don't know the value of the tension T, we just let Tx be equal to capital T multiplied by 0.857. And for Ty, all right, that's also equal to capital T multiplied by the sine value of 31.0 degrees. So we just let Ty be equal to the unknown value for T multiplied by 0.515. And the fact that the x component, Tx, this is the component of the tension T, okay, and that is directed up the plane, okay, for the car to remain in equilibrium, static equilibrium, that has to be equal to the x component of the weight W. So Tx must be equal to Wx. In short, Tx is also equal to 4.70 times 10 to the third power Newton. All right, that is using the concept of summation of Fx must be equal to 0. And we now have the solution for our first question, which is finding the value of the tension of the cable, capital T, right? So capital T, from what we have here, Tx is equal to capital T multiplied by 0.857. We can now calculate T, which is equal to Tx. The fact that we now know what Tx is, which is 4.70 times 10 to the third Newton, divided by the value 0.857, and our answer would be force capital T is equal to 5.48 times 10 to the third power Newton. Okay, rounded to three significant figures. This is our answer to the first question. The value for the tension of the cable exerted on the car. Right? So, we also identify the magnitude of the y component of the tension T now that we know the value of T. So, using that relationship, Ty is equal to capital T multiplied by 0.515, right? Or 5.48 times 10 to the third power Newton, which is the value of the computed T, multiplied that by 0.515, we will get as the value of Ty 2.82 raised to the third power Newton. All right? And to answer the second question, which is, in fact, okay, finding the value of the normal force Okay. The normal force is what is meant by question letter B. How hard does the surface exert on the car, referring to the normal force exerted by the ramp on the car, and that is the normal force F sub m. And that is just simply equal to the difference between the y component of the weight, or Wy, minus the y component of the tension T, or Ty. The fact that these are the only two forces directed along the y-axis. And for the car to remain in equilibrium along the y-axis, this is our equation. F normal is equal to Wy minus Ty. Substituting, we get 1.01 times 10 to the 4th Newton minus 0.282 times 10 to the 4th Newton. All right. So, our answer for this would be F normal is equal to 7.28 times 10 to the 3rd power Newton. All right, so that was the solution to this problem and the explanations. Now we're going to recap. We say that there are three major forces acting on the car. These are the weight W, all right, the tension capital T, and the normal force Fn. Notice that in the right triangle formed by the weight W, Wx, and Wy, all right, the angle 25.0 degrees is between Wy and W, all right. Wx can also be redrawn by connecting an arrow from Wy to W, that is the projection Wx. So it's now obvious that Wx is actually the opposite side of this imaginary right triangle, and that Wy happens to be the adjacent side of the same right triangle. Likewise, in the imaginary triangle formed by the tension T, the Tx, and the Ty, okay, um, Tx, the red arrow, is actually the adjacent side, okay, to the angle. All right. So while Ty, whose projection is indicated here by the broken arrow, happens to be the opposite side of the angle. So if we go over the solution presented earlier, started out with determining the weight of the car using this formula, mass times acceleration due to gravity, and we get this answer for the weight of the car. Likewise, in determining the x component, Wx, it was equated to W sine of the angle 25.0 degrees. Then substituting for the value of W, earlier calculated here, okay, and the value of the sine of the angle 25.0 to three significant digits, we got this answer. But the question is, why is sine of the angle 25.0 degrees was used here? The common notion is that when you're talking about the x component of a vector W, it is usually associated to the adjacent side. All right? Adjacent side, when divided to the hypotenuse, that should be cosine of the angle. All right? Now, if you remember earlier, it was explained together with the illustration that Wx happens to be the opposite side, all right? The opposite side in that imaginary triangle formed by the weight W, the Wx, and Wy, all right? So, Wx in that diagram was not or is not the adjacent side, right? Adjacent to that angle. In fact, it was the opposite. So that when you divide Wx over W, you are actually dividing the opposite side over the hypotenuse, and that requires using the sine of the angle. So there was nothing wrong in this solution. Likewise, for determining the y component W y, okay, we might say that Wy, since it is usually associated to the opposite side of the angle, it should have been W multiplied by sine of the angle. But just like in the case of Wx, it was also explained earlier that in that particular diagram, Wy happens to be the adjacent side of the imaginary triangle, right? Adjacent to the angle cosine, 25 degrees. So that when you divide Wy over W, you are in fact dividing the adjacent side over the hypotenuse. Hence, the use of cosine, the angle, was necessary. All right, so there was nothing wrong also in the solution for determining Wy. I hope that is clear. Unlike in the other triangle, imaginary triangle, formed by the tension T of the cable and its x and y components, okay, forming an angle of 31.0 degrees. Here, the Tx is actually the adjacent side of the tension T, so that the correct function is indeed cosine of the angle 31.0 degrees. All right. So, likewise for Ty happens to be the opposite side of that angle 31.0 degrees. So there's nothing wrong in the computation for Tx and Ty, okay, which led us to determine the value for the force of the cable capital T. Okay, it's worth mentioning here that Tx is equal to Wx. Okay, this is based on the fact that the summation of Fx is equal to 0, the fact that the car is in static equilibrium. All right, so only the two forces, Tx and Wx, are acting on the car along that imaginary x-axis. So they must be equal and opposite. All right. So using the equation here for Tx equal to T multiplied by 0.857, the cosine of 31.0 degrees, we were able to get the value for the tension of the cable. T equals 5.48 times 10 to the third power Newton. Likewise, for Ty, all right, this equation is based on this. All right, Ty is equal to capital T multiplied by the sine value of 31.0 degrees. Again, to three significant digits, it is 0.515. And what we got is 2.82 times 10 to the third power Newton for Ty. We use this in order to find the normal force Fn. Again, F normal is equal to Wy minus Ty, according to the fact that the summation of Fy must also be equal to 0, because only these three forces are acting on the car, all right, in the y imaginary, yes, in the imaginary y-axis. So that when we isolate the normal force Fn, we will come up with this formula, Wy minus Ty is equal to F normal, which gave us the answer of 7.28 raised to the third power Newton. All right. So these are the answers for the two questions, letter A and letter B. Okay. There was practically no mistakes in the calculations for these forces. It's just that uh, we went over the solution, all right, to clarify on the concept of using the cosine and the sine of the angle as applied in this problem. So I hope everything is clarified. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.